Yeah, I was saying that.
Thank you.
No problem. I was saying that I checked the number of views of the videos of today, and it was 10 a.m. I saw that more than 15 have watched the videos. It was the first time that you were kind of synchron.
Now we had some time to catch up during the holidays, so I guess that's why.
Yeah, good.
And also we tried, or at least me, I tried to do the lecture before the meeting at 11. So at
Yeah,
11.
that's a good idea. Yes.
But it's not that we have time to finish it like before 11. Sometimes it's like now it's 11. I'm done like writing the notes, but I also want to go through the videos more in detail and all of that. So.
Yeah, part of that is also more because always I want to do a perfect job, and I'm not satisfied until I know that there is not enough time to make it better. So I prepared the videos last night. It doesn't matter how much time I have. I leave it for the last night because, as I said, I want to do a good job.
Yeah, but they are pretty good. They are pretty good.
Yeah, thank you.
Hossein?
Yes.
I'd like to ask about the question 6 of the assignment.
Yeah, it's better to one of us share the screen. I can give you permission, then you share the screen.
Okay. Okay, is it visible?
Yes.
The question C, assuming the system is stable, what value of K should I take? Like for the system to be stable?
The type of system.
Yeah,
because the question is about type of system. Type of system is not a function of K.
Okay,
so it doesn't matter what K is.
So as long as the system is stable, then the system, the type is the same.
Yes. If what we should make sure is that the system is stable. But if we know that system is stable, then it's not a matter of K. It depends on the zeros and poles. So I don't want to give you the answer, but it's not related to K.
Okay. Another question, like I was just solving this one right before. And when the system is marginally stable, the Lucas, does it cross on the J omega axis?
Yes.
Okay. Just one.
Yeah. And by the way, can you scroll up? Because you have it open. The first question, yes, the first question was one of the questions of a final examination. I don't know what year. The same for question 2. The same for not question 3. 1 and 2 were in the final examination. Also 4. And if you scroll down,
yep.
Also 5 and also 6. So instead of other than 3, the other questions were in the final examinations last years.
Okay.
Just to give you an idea how the examination looked like.
For question 1, can I just use root Lucas to find the where the S passes JW axis?
Yeah, you can.
Okay, thank you.
You don't need to draw the root Lucas, but if you want, you are welcome.
Okay, thank you.
Can it also be done, because I did it by trial. I mean, I tried a couple values of K and I found
No, you shouldn't do that, because analytically means that you should solve it on paper, like theoretically.
Yeah, I did the question by paper, but then the value of K, I tried a couple values and I got it.
But this is not analytically. This is by simulation. Part A, when it says analytically, it means that you should solve it on paper, theoretically. using the Roth table or the other method I showed.
Yeah, but for that we need to find out the value of Ku, which is when we have a pure sine wave.
Okay.
And to do that, we need to kind of test until we get a sine wave.
No. This is what I'm trying to say. There are two different methods to find that pure sine. One of them is theoretically. It means that actually you go and find the case such that two poles are on the j omega axis. If the poles are on the j omega axis, that's for sure the step response would be pure sine.
Okay.
For yourself, you can test it just to make sure it is okay, but you don't need to. And the other method is by simulation or by experiment, but this question actually is asking you to do it theoretically.
Okay.
So just to make sure, then the wave will become sinus when the poles are in the j omega axis, no?
Yes, it becomes if the other poles of the closed loop transfer function are in the left side.
Okay.
Je weet niet of de hele stinger.
Somebody needs help. Any other comment, question? Let me.
Also, in the first question, when you ask to the second part of fine tuning it to reduce the percentage overshoot.
That one is by simulation.
Yeah, I know it's by simulation, but do we just reduce it by any factor, or like how small should it be? Because you can keep tweaking it until it's undershoot even.
Yeah, okay. It is up to you. I just wanted to show you that it is doable to change it by fine tuning.
Okay.
Yeah. Just showing that is enough.
Okay.
Maybe if you don't have question, I can show you a MATLAB function. Let me share my screen. And if it is possible for you, it would be actually useful if you do it with me. If you open MATLAB and repeat the procedure, because at some point it might be. I will record the video later and I will solve a problem from like start to the end. But also here it would be nice because I have your feedback. If something is not clear, I can explain more. Can you see my screen?
Yes.
Okay, let's open an M file and try to, one of the examples that I designed a controller for in the 2 days lecture, it was the transfer function was 1 divided by s multiplied s plus 3. So if we define s as a transfer function s, and then we had g is equal to 1 divided by s multiply s plus 3. And then we have a function in MATLAB is called SISO tool. SISO tool. And SISO stands for single input, single output. And if you type G, and then we can run the code. Right, let me find the right directory. It is a GUI. It will open a GUI for you, and then the rest you can do it graphically by mouse. You don't need to type anything more. You can design the controller graphically. My computer is slow. Okay, this is the window that will open. Let me close everything.
Hossein, how do MATLAB handle if you have a K value inside of the formula as well? How can you get MATLAB to understand what you mean?
What do you want to do?
In one of my equations, I want to check if I got the right value. So, but there's a K inside of it, and there's a 0 as well. I think it was question 4C or something like that. And I just wanted to check up if I got the right answer, but I couldn't get MATLAB to do what I wanted to do.
But still, I didn't get what you are looking for. But if you can define a symbol as K, the function is sims, and if you type here K, I'm not sure if this is the function. Yes, it is. Then K plus 1, it will give you K plus 1. You don't need to assign a number to K. You can work with K as a parameter. But I'm not sure if this one is what you are looking for.
Yeah, and then I had a 0 pole as well, but MATLAB couldn't handle it. I couldn't do the code for it to handle. So, but I didn't do the sims K. So maybe that's why.
Okay.
I will try again.
Yeah. Okay. When I type that function, this CISO tool of the transfer function, this window popped up. What we should do, this figure in the left is actually the frequency in the frequency domain. For now, just close it. And if you go to the view and this left-right view, so you see in the left side, you have the root locus. In the right side, you have the step response of the closed loop system. Remember, this one is the root locus of the loop gain, and this one is the step response of the closed loop system. Okay? And the controller, if you double click here on the controller is just a gain for now, but you can add 0 and pole later. For example, if I change the gain of controller, right now it is 1, and if you notice here, we have one open loop pole at 0, the other open loop pole is at -3, and this is the root locus. The poles are moving towards each other, and then they leave the real axis exactly at 1.5, -1.5 of course. Okay, so you see that when K is equal 1, the gain of controller is equal 1. So these red squares, it shows that where the closed loop pole is. So when K is equal 1, you have one pole here, another pole here. If you increase K, this pole will go to the left, the other one goes to the right. At some point, they meet each other here. And if you increase K more, then they will actually separate, and they will be complex, not real anymore. I can change K here. If K is 2, did you notice that they moved a bit towards each other? If I change it to 3, No, they have reached to each other and they have left the real axis. So I can do it and I can continue this procedure. In the right side, you can see online what is happening to the step response. Is that clear? Okay.
Yes.
It's not that different with when I am recording your video without any audience.
You get a yes at least.
Yeah, okay, thank you. It was a bit...
For MATLAB, do you need certain toolboxes to run this? Because it says four toolboxes are missing.
Really? Okay. Then my recommendation is that install it, because you do need that. I might even ask you to solve a question in the examination using CISO tool.
Okay. Can you show your code for 1 second again?
Yeah. It's just a CISO tool and then the transfer function.
Yes, thanks.
No
Because
problem.
it gives me some error in line 2 or line 3 for some reason, but yeah, I don't know.
Maybe you don't have the star between, maybe you're missing this star.
No, the line above.
This one. Okay, this TF function, it belongs to the control toolbox of MATLAB.
Okay, yeah.
And control toolbox is one of the toolboxes that will install by default. So I will be surprised if the control toolbox is not installed.
Interesting. I'll figure it out.
Okay.
You can also always add it afterwards.
Yeah.
Toolbox. So just search it.
Okay, I was talking about this root Lucas, and I said that you can change the gain of controller and you can see what is happening to the step response. Also in the right side, if you right click and in the characteristics, you can, for example, select the settling time, and you can see that what the settling time is. So it is almost 3 seconds.
How did you select it again?
If you right click, characteristics, and then settling time.
Okay.
Do you know where this is it actually, the question is that, is it what we expected for the settling time? Because we knew the poles. Is this 3 seconds, or does this 3 seconds make sense? Okay.
I honestly don't know. Like,
because the settling time is 4 divided by the distance of the pole to the j omega axis. This is j omega axis, and distance of the pole to the j omega axis is 1.5. 4 divided by 1.5, it should be something like 2.8, 2.7. So it is actually what we expected.
Yeah, 2.66.
Yes, yeah, you can click on that. Yes, but what you should okay, I should emphasize that maybe this 4 divided by zeta omega n, 4 divided by the distance of the closest pole to the imaginary axis, is one of the most important equation in control. It's really important because it gives you an idea of how fast the system is. So you should find the closest pole to the imaginary axis, and being close to the imaginary axis, it means that that pole is dominant and it is slow. Because if you move the pole far from the imaginary axis, it means that you are making the system faster. So for each system, actually, it is very important to know. And if you have the settling time, let's say you for a room, you switch on the heater and you measure the temperature, and for the temperature it takes, for example, 10 minutes to reach to the final value. So that this 10 minutes is the settling time. Roughly, you can say that the system has a pole at 4 divided by settling time, because 4 divided by settling time is zeta omega n. Also 4 divided by zeta omega n is settling time. Okay, you can switch them. So if you know what settling time is, you can guess where the pole is, and vice versa. If you know the pole position, you can guess the settling time. It's very important in control. Anyway, the controller
But this
here
only
is,
gives you, this gives us exact value or an approximation of what the settling time
if
would
the
be.
system is second order, is the exact value. Okay, but I should be careful about this exact. But with a good approximation. But if system is of fifth order, then it is really an approximate value. But in this case, because we have a second order system, the approximation is not that much. It's quite close to the exact value. Okay. And this is, as I said, this example is part of the lecture of today. And I have asked you, or not asked you, I have showed how to design a controller such that settling time is 1 second. Okay, the settling time is supposed to be 1 second. But here you can see that settling time is about 3 seconds. If you want to make the system faster, we should move the poles to the left. But changing gain of controller, it doesn't move the poles to the left because the poles are going up and down. Distance to the imaginary axis will stay the same. Is that clear?
Yes.
What we can do, and I have shown you in the lecture, you can actually add 0 and pole to the controller. If you double click on C and then this window is open and right click here, you can add pole and 0. What I have done in the lecture, I have added a 0. Do you remember where the 0 is? Have you watched
It was in the same spot as the other pole to cancel it.
Yeah,
Yeah,
in the first part it is at minus, well, it's minus 5.88, which
yeah,
is
that was
9.
that was the pole. But 0, but you're right. I have given you 2 solutions. The first one, 0 is at -4. Okay, and pole, if you right click again and this time you add a pole, I will not specify the exact value for pole. Just select some random number here, for example 7. Then I will show you, actually I could have solved the problem using simulation, using CISO tool. So here, not only I'm confirming the design of controller in the lecture, I'm also showing you how you could have done the design from the scratch using simulation. Just to get the representation of the controller as we expect. Where should we go? Yeah, okay, this one is what we expect here. But when you double click on C, it is different with what. There is somewhere that we can change the representation. I don't know, maybe here in the preferences. Yes, I think it is here. Options, yes. If you click on this preferences and then 0 pole gain, select this 0 pole gain and press OK. Now if I open the controller, you will see controller has 1 0 at -4 and the pole of controller is at -7. I haven't designed the pole yet. I'm going to show you how to design it. So if in the root Lucas, if you right click and you have one item is called design requirements, and if you select new, okay, here you can, for example, specify what should the settling time be. So settling time should be less than 1 second. It is exactly what I have asked you to do, or I have done in the lecture. So press OK. If you, I don't know if you can see that, but it is a bit shaded. Part of the space is shaded. It means that the pole should not be in this region. It is a bit different with what I do. In the lecture, I do the region of interest. So basically, I shade the region that is interested for you. But in MATLAB, is the opposite. The shaded part, it is the part that the poles should not be in. But that's okay. We know what we are doing.
I can see that the asymptote or the line that is dividing it is not exactly located on 4. Is that a thing of the software, or is it actually a little bit next to 4?
It's because, yeah, exactly. That's a good point. It's because this 4 divided by zeta omega n is not an exact equation. It is an approximate equation, but it is not that far. Yeah, it was a good point. And then the next, again, if you select on the design requirements, because in the lecture, there was another requirement as well. It was percent overshoot, and this one is supposed to be less than 9. So type 9 here, press OK. Is that clear what I'm doing?
Yes. And
If
from
you
here,
have,
we only need to adjust K, right? To get
no,
it to
it's still
approximate.
the pole is not adjusted. Why the pole is not adjusted? Because I selected pole at -7, but in the lecture, I calculated the pole such that the root Lucas is passing through this point. You see that it's not passing here. Okay. How to make the root Lucas to pass through this point? In the lecture, I have explained that when we have these two requirements, usually we select the corner points as the desired place for the closed loop poles. It means that the root Lucas should pass from here. To do it, to make it happen, you can actually click on the pole and hold it and then move it to the left. I'm actually moving the pole to the left, and whenever you get the root Lucas to pass through that point, then it's the right position for the pole. Is that clear? Basically,
Yes.
I could find the pole position such that the root Lucas is passing here. I can see what the pole is roughly 9.67 because I checked that by eye. But in the lecture, I calculated that. I think it was more or less the same. But a small deviation that you have here and in the lecture is because if you zoom in, maybe it's not exactly passing through the point. Or also in the lecture, for example, the angle, I said that the angle is 53 degrees, which is not exactly 53. It is 53 point something. I just removed that float. So this is how to find the pole. And if you want to see how to find the gain, you can click on the one of these squares and then move it to the, if you click on the third square, you can move it to the right. If you click on this one, you can actually move it to the exact point that you are interested. So if you increase the gain, by moving this, actually I'm increasing the gain, I'm adjusting the gain. So you can select the gain such that the pole, the closed loop poles, Roughly, we are there. As far as I remember, in the lecture, I calculated that it was 50, I don't know, 53 point something, or
we are checking it.
I have a question.
yes, I can open the lecture as well. Yes.
Yeah, in the MATLAB, can you come back when you're done with
Just
this?
give me a second to see.
Yes.
53.5.
Yeah, thank you. Yes, 53.5, and the pole was 9.82. This small deviation is that because we are checking by eye. If you want the exact value, also you can type in here 53.5, and the pole was 9.82, if I remember correctly.
Yeah.
9.82. Yeah, and this, okay, if you check here, actually it is not exactly at the line, and the reason is that this line is not exactly at -4. It is slightly to the right. But this is a small variation, it doesn't matter, so it is still okay. Sorry that, let me finish this one as well, then I will come back to you.
Yeah, no, it's fine.
And here, if you check, the settling time is less than 1 second, and the percent overshoot is not 9%, it is a bit more than 9%, because also you can right click here, design record, no, the characteristics, and then peak response. If you check the peak response, it is 1.15, which means that the percent overshoot is 15%, but we were expecting 9%. Do you know why?
Because the gain is increasing, that's why. Right?
What do you mean? No, what do you mean increasing?
The gain is increasing, so the percent overshoot is increasing, right?
No, there is another reason for that. The reason is that these equations are written for a second order system, but the system you have is third order because you have 2 poles here and 1 pole here. So we have a third order system, and even though we have 2 poles here and we are expecting to have 9%, but because of the third pole, there's another pole here and also there's a 0 here. They changed the specification to some extent, but here, if you want to get exactly 9%, then you can move the zeros and poles slightly and make it actually what you exactly want. So if I move the 0 a bit to the right, just to show you that you can improve it. It is getting less. It's now 12% and the setting time is less than 1. Okay, so by moving the 0 to the right, or you could also have some other options.
But Hossein,
yes,
could I can see that for in the region of interest, the we have 2 poles that they are outside of the region of interest.
I have brought them inside now.
Yeah. So now it should be less than 9%, no? Or what?
No, because the system has 3 poles. Those equations are for 2 poles, and we are only in the design. We only take care of these 2 poles. But the third pole actually is also affecting the system.
So it doesn't matter if the third pole is in the region of interest.
It's a very good question. Because for that specific gain, the third pole is here. Can you see the square here?
Yeah.
And it is very close to the 0. Okay?
Yes.
Because you have a pole and a 0 very close to each other, they more or less they cancel each other. So they have a slightly, not much effect on the final result, but that you can see the effect now. So
yeah, okay.
Yeah.
So if it would be exactly
Yeah.
Sorry.
If there wasn't any zero here, then the effect was much more. But because of the zero, it is not. It is actually negligible.
Okay.
It's a very good method to design a controller for any system, because at the same time you can check the step response, you can see if the conditions are fulfilled, and you can refine the design. But what you should notice is that even though you have access to this CISO tool, you should still be able to solve the problems by hand, because if you don't do that, or if you are not able to do that, then you are not able to analyze what you get. Right now, you ask me many questions that why, when the poles, for example, are here, why we don't get the same, or why we don't get, for example, the person overshoot less than 9. So these questions and some similar questions, if you don't do the design on paper, if you don't get master in that, because MATLAB is sometimes dangerous. Whatever you type in, it will give you some result, but you should actually make sure if it is a proper result or not. Okay, what was your question? We can now.
Yeah, actually, I think I know the answer now. My question was about the percent overshoot, because you said like we need to move the pools to the borders of the region of interest. Then when I looked to the step response, I found that percent overshoot increasing too much. That's why I'm asking. Maybe this thing is not valid for all the systems. To have a big percent overshoot, but then I found out that because of the zero, when you moved it to the right, so the percent overshoot get lesser.
Yes.
Yeah.
But also for you and the other students that are working on the inverted pendulum, this CISO tool is a very nice tool to design a controller for that system. And at some point, because we are not finished with this lecture, designing controller using Ruth Lucas, also next week I will have some more examples, and I will show you at some point we can also design a PID controller using this tool. Other than this week, we have 2 more weeks, and next week part of the lecture is related to this Ruth Lucas, designing controller using Ruth Lucas, and then we will have the frequency response. Any other question?
Yes. So when using the CISO tool, if it uses equations that are actually meant for second order systems, wouldn't the numbers that we get for a third order systems then be wrong in like when you want to apply them in reality?
Yeah, to draw this region of interest, it uses the equations that we have for a second order system. But even in this third order system that you're seeing on the screen, still we can approximate this third order system with a good approximation to a second order system, because we have 2 dominant poles. But if it happens you have a system that the couple of poles, like the 2 poles, are not dominant compared to the third pole, then CISO tool, what you get here in the step response, it actually correct. It is correct. But what you get here as a region of interest, as I said, this one is drawn for a second order system. So what happens is that even though the poles are in the region of interest, the response is not what you expect. But then you can refine it. What is nice about this tool is that the step response is not for a second order, it is for the real system. Even if it is of 10th order, it will give you the right response. In the video I will record for the simulation, I will show more features of this CISO tool function.
Very well, thank you.
No problem.
And I have a question about the lecture.
Okay.
Could you open it or?
Yeah. So let me share the screen again. Which page?
Page 4. Yeah, so my question is why here the desired pole is only -1 plus j 1.33 and not -1 plus minus j 1.33?
Both of them are the desired poles. But if your question is about how I have found k, if you only apply one of the poles is enough. You know,
Okay,
you have a polynomial, and this polynomial has 3 roots, or in this particular case, it has 2 roots. So it doesn't matter which one you select, you will get the same k. You can also try the other one, -1 minus j 1.33. If you apply that one, you will get the same k.
Okay.
Yeah.
Yeah, and also in page 8.
Yes.
Yeah, so again, you can see in the down part, you only draw in the graph, you only draw a triangle for, like in the green line, in the vertical green line, you only draw a triangle.
Yeah, there should be another one here. Yes, there should.
Okay, okay.
Yeah,
that was it then. Thanks.
No problem.
Hussein?
Yes.
I also have a question, but it's from a previous lecture. It's okay if I ask you?
Yeah, sure. Let me find it.
It's about the Ziegler-Nichols second method.
Oh, about PID?
Yeah.
PID or Routh-Lucas? Because we had Ziegler-Nichols in both.
PID. It's because I understand how to do the second method by testing in Simulink, but I don't really understand how to do it analytically because there is no example of that. So I'm not sure how to do it.
I did an example, didn't I?
No, there was no example of analytical analysis. I mean, you got the k value in Simulink and then you showed how to do it, but not how to get the value directly here.
No, in Routh-Lucas I showed you.
Yeah, in Routh-Lucas, yeah, but not in Nichols' second method.
Yeah. In Routh-Lucas I showed you an example. Because I left it for Routh-Lucas, I wanted to give you an intuition why we can use the Ross-Horowitz table. Yeah, this is an example I have done. Can you see that?
Oh, okay.
Yes.
And with 2 different methods, I showed you how to calculate KU and TU. It was using the Ross table and also using another method, which is also some of the students actually, they prefer to use this.
Oh, okay. So yeah, that's all. That's also my doubts.
I have a question regarding the closed loop. When we calculate KU and W for the closed loop, we get the we have to get the transfer equation, right? Of the closed loop system.
One more time, sorry.
Yeah, to get K,
okay,
the value of K, we need to get the equation of the closed loop system, and then we get use the denominator of the transfer function, and we make that equal 0, right?
Yes.
But should that be of the when you make the transfer function is it's KGS HS divided by 1 plus KGA HS.
Yes.
If I just take 1 plus KGS HS, is that the same as doing the whole thing?
Yeah, it's a very good question. It's a very good question. I'm glad you asked. When you form this 1 plus KGH equals 0, it is not a polynomial. It is a transfer function. It is a fraction. Okay, it has a numerator and it has a denominator. And when we set it to 0, I say that, okay, just set the numerator to 0. Why I don't care about the denominator? Because the denominator of that will be cancelled with the denominator of the closed loop transfer function. Because this 1 over 1 plus kgh is the denominator of the closed loop transfer function. Does that make sense? I don't know, maybe I can open Paint. So here we have G, H, or KGH. Okay, that's because I don't have any mouse. And then in the denominator, we have 1 plus KGH. Okay. And if you notice here, KGH is not a polynomial. It is by itself a transfer function. Is that right? It has a numerator and it has a denominator. The
Yes.
same for this one, 1 plus kgh. It is also another transfer function. So what you have here, you have a transfer function, you have a fraction that has a numerator and denominator. Also, you have a fraction that has a numerator and denominator. But the important point is that the denominator here and the denominator here, they are the same. So basically, when you form the closed loop transfer function, you can cancel out the both denominators. And what is left is the numerator of kgh divided by numerator of 1 plus kgh. And that is why when I form this 1 plus kgh, I only care for the numerator. Is that clear?
Yeah, that's why you usually get K plus GH equals 0.
No, I always write 1 plus kgh equals 0, not k. Let me also find the lecture. Maybe today's lecture I can. You see here? I write 1 plus kgh is equal to 0. And kgh is this fraction. So 1 plus this one equals 0. So it would be this divided by the denominator. Is that clear?
I think so.
If you make the common denominator here, in the numerator we have s plus 1 multiply s plus 2 multiply s plus 3 plus k, and then divided by this denominator. But when I set it to 0, actually I just write the numerator. And as I said, this denominator I don't use it because I know that this one will be cancelled with the denominator of the transfer function, of the numerator of the transfer function.
Yeah, I see.
Anyway, this one is equal to 0. It means that numerator is 0. So it's by itself is also correct.
Okay.
We have 2 minutes left. Okay, because I have other meetings that starts from 12:30, so I should finish this. It's being recorded. I will send a link on Blackboard. Okay, if there is not any question, so have a nice weekend. And for those of you who have the semester project, we will have other meetings as well. See you.
Thank you, you too.
Thank you.
Thank you. Goodbye.
Bye.
Thank you.
Bye.